Tell your partner, what are they? Is it a question or an answer? So both of these affect the Coulombic attraction. What's one of them? Yes? Zeph. The effective nuclear charge, which breaks down into two things. Z, what's Z? Protons. And S, what's S? The core electrons. What's the other thing that affects the periodic trends? Occupied shells, the number of occupied shells. Now, when we're talking about Zeph, is that a horizontal trend effector or a vertical trend effector? Chat with your neighbor about that, because I heard a lot of horror is vertical. Yes. Okay, Zeph. Horizontal or vertical? Horizontal. And number of occupied shells? Vertical. Okay, so we're going to look at how these things affect electronegativity. How good is that electron at pulling, or sorry, that atom at pulling bonding electrons towards itself. So as we go across a row, going that way, so we want to be talking about our Zeph, right? And you want to start by, and I have to be honest with you, I went looking for AP questions yesterday, and they're sort of few and far between in terms of, like, they're not, like, periodic properties are tested sporadically. So anything could show up, but it might never show up. So any of them, it could be whatever. But what I did notice is that the trend is towards longer explanations. Okay, when I looked at the 2010 exam, the one question I found, it was a pretty sparse answer. The 2018 exam, it was more explicit in terms of like spelling out everything. And then the 2021 exam, they were like, yeah, it's not enough to say Zeph increases. Like that would just not cut it. Okay, so you would need to say, what would you want to start with? What's like the starting point for what's happening across a row? Protons increase. What else happens across a row? Core electrons are constant. And that leads to and if it was the first time I said it on a test, I would write this as effective nuclear, just to prove that I know what it means. You know what I mean? Okay. Yes? Like writing number p plus increase? Like that? Probably. I'm not 100% sure, but probably. Okay, now, so that is, so once you've got that, you can say, what can you say? How does this relate to electronegativity? Tell your partner how this relates to electronegativity. Don't read it. We're talking about how this affects electronegativity. So we have talked about the number of protons. We have talked about the number of core electrons. We have talked about Zeph, and we have talked about the Coulombic attraction. Okay, so those are 4 things that you want to have in your answer. Yes? Now, have we mentioned anything about electronegativity yet? No. So, and then I would say maybe since electronegativity is the ability to pull bonding electrons towards itself, yes? Now let's see how that answer compares to what I wrote on the actual sheet itself. I'll bring this back in just a second. Okay, what did I write over here? I said the number of protons, Z, increases. Added electrons go into, I'll bring it back, don't worry. Added electrons go into the same energy level, so I said a little bit more. So the shielding, S, core electrons remains constant. Therefore, Zeph, which is Z minus S, increases. Since Coulombic attraction is directly proportional to charge, Coulombic attraction increases as Zeph increases. Therefore, bonding electrons are pulled more to the nucleus more strongly. Therefore, electronegativity, the ability of an atom to pull bonding electrons towards itself, increases. So I pretty much said the same thing, yes? Not exactly the same words, but I feel like both of those would probably get full credit. Now, you're going to be sad when you find out like how many marks you get for something like this. It's usually like 1 mark. I don't even know if they give you half marks. But, you know, so when you're doing these questions, apportion your time resources well. Yes? If there is something where it's like, I can get 1 mark for writing an electron configuration, 1s2, 2s2, 2s2, get done. And I can get 1 mark for writing all of this crap, like, do the ones where you can get those cheap, fast marks first. Okay? Definitely, you know, I mean, it's nice to be able to explain this, but if you're running out of time, this would be a question where you're not going to get as much bang for your buck, right? Yes. How many questions are on the test? There are 60 multiple choice questions to be finished in 90 minutes. So it's 1.5 minutes per question. And then there is written response, which is also 1 hour. I believe there are 6 questions. I could be wrong. I'll have to look at that. It has changed over the years. No, so this would be like a written response. Maybe 1 mark, maybe 2. It just depends. There's questions are, what they do is they give you a 10-minute question, or sorry, a 10 mark question. You should be able to finish in, I think it's 20 minutes. I have it all written down. I'll figure it out for you. Okay, but I do know we'll worry about that later. Okay, that's next year. Yeah. Now, shall we? Would you guys like to try explaining the trend in electronegativity as you go down a row? Try it. Don't look at what I've written. Try explaining or down a column, I'm sorry. Down a column, down a group. How we doing? We good? Okay. So what's one of the first things we should explain? Number of occupied energy levels or occupied shells. Does what? Increases down a group. Yay, okay, what's next? Yes. Okay, so what we want to also say is we want to say that higher energy levels are further from the nucleus. We'll do that as well. You can attack this from two different directions. You can do one first and then the other or whatever, yeah. And therefore, bonding electrons are farther from the nucleus. Yes? Okay. What should we be talking about next if we're following this path? F equals K Q over R squared, where R is the distance between charges square. Well, I mean, yeah, you're talking about, in this case, you're talking about atomic radius, but this applies to things where it's not a radius. You know, you've got two charges. Yeah, and if there's two separate things, it's obviously not the radius. So, but maybe that's where it came from. I don't know. Anyway, so therefore, as distance increases, F decreases. Therefore, what's next? Electronegativity the ability to pull bonding electrons decreases. Now, if you had written all that, you would probably get full credit. If you wanted to, if you're like, oh, I have lots of extra time, oh, you could then talk about Zeph and say it doesn't matter. Why doesn't it matter? Because they cancel each other out. The added protons, the number of added protons is the same as the number of added core electrons as you go down a route. That's true, that is true. Yes. Do you guys know how often I have written this explanation in the last like 7 days? It's because for every trend, I have to write it in the thing and in the answer key. And then I write it here. I do sometimes. But you know how it is when I copy paste, sometimes I get things wrong, right? So, and sometimes I try to give you different words because sometimes different words work better for different people, right? So sometimes I just try and think about it fresh and try it fresh. Like here, I've been using a lot more symbology rather than words. Okay, so how are we feeling about electronegativity trends? Pretty good? All right. Let's see if there was anything else. The only thing is how it affects bonds, and I think we've already talked about this a fair amount. Polarity you don't need to know for this test, okay? But you should know that if you have a moderate difference, you'll end up with a polar covalent bond. If you have no difference, so this is a moderate difference, in electronegativity. If you have no difference in electronegativity or minimal, so polar would be a moderate difference in electronegativity. Non-polar would be a minimal or no difference in electronegativity. Yes? So minimal is up to 0.4. Yeah. And to be honest, and I don't know if you were here for that discussion, that 0.4 is set pretty arbitrarily. There's someone was like, oh, I think it should be about here, right? And things that fall right near it, you know, is it more ionic or is it more polar or is it more non-polar? It's hard to say when you get to those borderline cases. Yeah. And then finally, they didn't have one of the pictures with the little, you know, angry faces. I actually like these ones better. We have atom A has a weak pull and atom B has a strong pull. We have a big difference in electronegativity and we get ionic bonding where the electrons are transferred. Yay! And you guys are going to take a moment and you know what? You don't need to do these because we just did those. Okay, you'll do that later, like maybe when you need more practice, but you're going to do number 4 while I print out one more of these things, okay? Because I think we might get through first ionization energy today. So just do number 3 and 4 for a moment. Why is this never here? Oh, there it is. Okay, thank God. Whew. Well, they're organized to a certain point, and then there's things where I know that this file is in stupid computer because it was on the stupid computer that like sort of imploded, and it's in the active biology folder because that's where it got stuck. So in my head, I also have levels of organization that don't make any sense whatsoever. Hmm? Are we finished or do we need another minute? Are we done? So for number 4, does anyone need another minute? Okay, who has the greater electronegativity, calcium or gallium? Number B, lithium or oxygen? Chlorine or sulfur? Bromine or arsenic? Barium or strontium? Oxygen or sulfur? Oxygen, hooray! Okay, first ionization energy. Oh, here, don't look at it. I would like you to write the definition for first ionization energy to the best of your ability. I know we only mentioned it last day, but see what you can dredge out of your brain. Don't be shy about getting extra paper if you need. There's some at the back there. Second ionization energy will be the energy needed to remove the second electron after the first one's already gone. And then the third one will be the third one once the first two are already gone. We'll get to it. We'll get to it. Hi.
What's the deal with this? Why is there 2 plus there?
Because there's a 1 plus here.
So if there's a plus there, that's plus ionization energy.
We'll talk about it. Don't worry.
Okay.
Yeah. Nope. No. No, don't even go there. Okay. It is the energy required to remove an electron from the highest energy level of a yes. Thank you. Yes, you. Sounds français. So let's just take a quick look over on our previous page here. So here we go. Here comes the ionization energy. Do you see how our highest energy level is no longer filled? Okay, although that would be like for, say, sodium, where it only had 1 electron in that level. If we say ionization energy, we mean first ionization energy. We should always say first ionization energy, but we're not always that lucky. First ionization energy. You're ripping out the first electron. Once the first electron is gone, second ionization energy would be taking out the second electron, but that first electron has to already be gone. So you're starting now with a plus ion, and now you take out the next one, and so you end up with a 2+ ion. And now that you have the 2+ ion, you'll take a third one, whatever one's the next highest, and you'll take that one out, and so on and so forth, until you run out of electrons. Yes? Okay. So what is our trend across a row? These are all being removed from n equals 2. Yes? We are on page 33. Page 33. I should make a little border around each page that just has the page number. You don't have a page 33. Okay, so you need to go. Okay. So you're one of those poor people who I was like, why are there so many leftover pages at the back here? Let me see what we can do for you. No, no, no. You probably don't. Okay, so what has happened is we have run out of copies, so I'm going to print a couple more copies, but while I do that, you are going to try to explain the trend in ionization energy as you go across a row in terms of the same like you did for electronegativity. As you go across a row, explain the trend in first ionization energy. And while we do that, I'm going to print out pages, whatever. Godwin, how much of it do you need? Do you need like the whole thing? You need 32 and 38. Okay, I'm just, yes? I cannot hear what pages people need. So I need 32 and 38. Yes? You need 33 to 38. Okay. Yesterday's. Ah, okay. That's all right. Yes? You need 33 to 38. Okay. And you need same thing. Oh, so you guys are just missing yesterday's stuff. Well, there should be more of those, but I don't know where they are. So are you guys actually doing what I asked you to do, or are we all looking at our GoPro Evan, there is no page 30. Okay, there we go. It's recording again. Excellent. So as we go across the row, what should we talk about? Number of protons increases. Yay! Number of core electrons stay the same. Oh, hang on. It doesn't stay the same. What am I writing? It increases. Silly me. And look, I'm writing this again. How many times is this now? It's probably like 18. The core electrons. Oh, that's special. Okay. They're like the supercore electrons. So, therefore, or actually, as charge increases, Coulombic attraction increases. And I would be very, very tempted to write Coulomb's law here, because otherwise you have to start talking numerator and denominator. I don't know, they mention stuff like that, and I'm like, oh my God. So it would be just easier to write F equals KQ over R squared, right? Because then you don't have to like write a whole bunch of blah blah, and that just takes a minute, right? Like a half a second. Coulombic attraction increases. Therefore, what can we say about those outer electrons? Are held more tightly. Therefore, it requires more energy to remove, huh? Oh, wrong E. It does not require more electrons to remove an electron. It requires more energy to remove an electron. Therefore, ionization energy, the energy needed to remove an outer electron, increases. It's the same explanation over and over and over again. Do we want to do it for going down a column? Or you think we're good? Do we want it down a column? Okay, go. Do it down a column. I've put this in brackets because this may not be your most important point, right? I'm just kind of getting it out of the way. Have you guys seen that little video? There's a video of this guy who, like, his professor told him they weren't allowed to bring computers to their laptop to their class. And so he brought the typewriter, and the professor's like, blah, 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 tack, 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 tack. Ding! Tack, 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 tack. That was awesome. I love that. I was like, oh my God. I love that. So good. So higher energy cells are further from the nucleus. Yep. Yep. I've actually had typewriter keys get jammed. Typing is so much fun though. That was my favorite class in high school. Typing 9. Like total no stress. There was no homework. Like you just went into class and you typed. I mean, you were supposed to go home and practice, but if you were good enough, and you know, I played piano, so my fingers at least moved decently, right? I'm not super fast, but you know, they moved okay. And so I would like I'd be like, tuck, 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 tuck. And my two friends were in there and we chatted a lot. And it was just like a total stress-free environment. It was amazing. What? Yeah. Yeah. I told my son there was a keyboarding class at a school. He wanted to take drama, and I said, you are welcome to take drama as long as you spend this summer before grade 9 learning how to type. So I put a little cardboard box over his hands and got a whole bunch of like typing ninja programs and whatever they were. And yeah, so he had to like learn how to type. Anyway, yes. Okay, and I've been trying to put them in a playlist too. So there's like a Chem 11E playlist if you're interested in such a thing. It helps me find them. If you find one of the videos, it should say in the playlist or whatever. I have like, I think maybe 4 subscribers or something. Of which? I have 57. Ooh, that's exciting. I thought it was 4. It really, I feel like maybe the 57 came from COVID, you know, when we were online. Yeah. Anywho, lower on the periodic table, electrons in the outer shell are held less tightly and therefore require less energy to remove. Now, if you're looking at views, a lot of those are just me trying to go in and find something. So a lot of them are just me looking at my own videos, right? Because I'm like, where is it? Okay. So are we good with this? Are we exhausted by it? Because I know I am. Okay, okay. So let's see. Oh, and there's like a little fill in the blanks if you want to, like over the weekend, if you want to review for yourself, you can fill in the blanks. Okay. And then there's some exercises. Yay, well, whatever. What's 10G? Oh, electron affinity. Should we just take a quick look at this before we go today? Okay. I desperately want to say that I don't think electron affinity will be in the exam, but I think it could be because they put it back into the curriculum. It is a confusing one though, and it's poorly explained everywhere. I feel like you would actually need like a 3rd or 4th year chemistry textbook in order to get a good explanation, and those are not just lying around online. So the easy part of it is it's almost like the opposite of ionization energy, but not really, because it's not like you're putting an electron into a positive ion, you're putting an electron into a neutral atom. In general, these are going to be negative values because electrons like, ooh, look, nucleus, I want to get closer to that. Yes? So when we say we have a large electronegativity, that means we have a large negative number, okay? When we say we have a small EA, that means either we have a small negative number or a positive number. Yes? Yeah.
So for grade 12, they didn't learn it.
Oh no, they may have learned it. Because we've still been teaching it because it wasn't explicitly, it was not one of the explicit exclusions from the curriculum. It was just kind of like, oh, they don't mention it and they haven't asked about it. Maybe it's not there anymore. You know what I mean? But now they put the words back in, so now we're like, okay, well, no. Okay. So if we have a small electronegative or electron affinity, they all sound the same after a while. We have a small negative number, or we can have a positive number. Okay, and for your noble gases, in fact, what can you see about the noble gases? Their electron affinities are more than 0, which means they are positive, which means they have a low electron affinity. Okay?
So shoving
Yes. Yes. Yes, only available by human hands. Okay? So helium. Helium does not want an electron. It's got a full outer shell. That's stable. I don't feel like that's the explanation that AP wants, but I could not find another explanation out there. It goes into a shell that is further away from the nucleus. That's not as happy as going into shell number, like if you're going along period number 2, every electron that you're throwing into there, into lithium, into beryllium, whatever, it's going into shell number 2. But the moment you get to neon, you're putting that electron into shell number 3. So that's why I feel like they might ask you something like, why are the noble gases higher? Not why are they greater than 0, but why are they higher in electron or lower? It's always so hard because it becomes positive, but it's a lower. Why do they have a less electron affinity than the halogens? That would be an answerable question, because you could say that electron would have to go into a higher energy level than the corresponding halogen. That would be answerable. Whereas, why are the noble gases positive electron affinities? That I feel like I don't know that they could ask you that. That's too vague and weird. Okay? There's a few others that are positive. Beryllium's positive. Magnesium's positive. Why do you think that beryllium and magnesium might be positive? Yes. That's right. We've just finished filling up the S subshell. So that next electron that we put in is going to have to go into the 2p subshell, which is further out. So for the same reason that the noble gases don't want that extra electron, similarly, beryllium and magnesium are like, oh, it's not as favorable to go into that higher energy bracket, yes. We kind of do. We do. It's not positive, but you can see that calcium is a lot lower than potassium, even though the overall trend is upward across the table. So the alkaline earth metals, in general, have unusually low electron affinities. Yes? What's up with nitrogen? Yeah, what is up with nitrogen? Think about that one for a minute. Yeah? Yeah, because we're halfway through. Nitrogen is already half filled a p subshell, right? So it's like this. La 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 la. Where does the next one have to go? It has to pair up, double up. Not so happy because now you've got two electrons. There's electron-electron repulsion. It makes it less favorable. Yeah? What about phosphorus? Phosphorus, same thing, right? Because it's also got 3, and then the fourth, that extra one has to go in as the fourth electron. Ah, why is it so much higher than nitrogen? Hmm. Maybe because it's just got more space to move around because it's bigger. I don't know. Like I said, there's a electronegativity. If you look at it, it looks like a real patchwork quilt of like different colors representing them. So you're not going to have to explain anything other than those sort of major anomalies, like the alkaline earth metals tend to have a lower electron affinity. The noble gases tend to have a lower electron affinity, and group 15 tends to have a lower electron affinity. So those are the ones where you might actually have to do it. We'll talk a lot more about electron affinity next day. I just wanted to kind of give it to you there. I feel like we've talked a lot this class. If you just want to go home and let it sit in your brain for a while, I think that might be nice. Yes? Yeah. Yeah.
I wrote all the right answers, but it didn't write it in pie form. I wrote what is it in pie form, and then I could have just divided it by 5 and multiplied it by 4. So then I got one plus positive. And then there's got right on the dot. And then one of them is so free. The answer is so free. I just need to think hard. You have multiple choice questions combined with one. It's like it's a little bit why do it catch up? You want Nathan to
Why do these want to add? I assume they don't really want to
They
add
don't really want them,
But
but
they can,
but they can, and the fact is that they don't want them nearly as much as any of the these guys want them. So these guys will be like, I'll take it away from you, right? Whereas these ones, it's kind of like if somebody shoves an electron at me, I'll like be like, okay, well, whatever, right? Yeah.
So I assume you'll eventually learn how to calculate the.
Electron affinity?
Yeah, no, it's
Nope.
there.
It's just there. Yeah, that would be like high level physics.
So
Yeah.
you should just like know what it means.
You should just know what it means and kind of the overall trend, and then we'll talk more about the exceptions to the trend as well. Yeah.
I drop my stuff here while I use the bathroom.
Okay. And I'm just going to do the same thing as I did yesterday. I'm going to like, yeah, perfect. We can just do that again.